In this video, we'll be going over LeetCode problem 366, find leaves of a binary tree. So in this problem, we're given the root of a binary tree, and we want to collect the tree's nodes as if we were doing the following. So first, we want to collect all the leaf nodes of the tree. We want to remove those leaf nodes, and then we want to repeat the process. So we want to collect the next set of leaf nodes and remove those. So let's take a look at an example really quick, and hopefully this will make some sense. So let's imagine this is our tree over here. So here's our tree, and it has 5 different nodes. And so in order to do what they're asking, we want to first collect all the leaf nodes. So we want to collect this 4. We can put it over here. We want to collect this 5, because it's another leaf node, and then this 3. So those are leaf nodes, and we'll group those together. Now that we've collected those, we want to remove them. So let's remove the 4, the 5, and the 3. And then let's repeat. So we look for more leaf nodes. This time 2 is the only leaf node. So we'll add 2, and then we'll remove it. And then finally, we have 1 leaf node left, this 1. So we'll put this 1 over here, and then we'll remove it. And then altogether, this gives us a vector of vectors, where each kind of smaller vector contains the sets of leaf nodes. Now, the question is, how do we actually get to this final output? So let's actually take a look first at our tree, and let's take a look at how it relates to this final output. And here we're going to want to use a notion of the height of a tree. So let's imagine that each node is actually its own tree. So this 4 over here, let's imagine that it's its own mini tree. And if we look at this 4, we want to consider the height of this tree, this mini tree over here. And the way to determine the height, we want to look at the children of this node and see how many levels of children do we have. And so in this case, this 4 doesn't have any children. So there are actually 0 levels of children. And so if we want to note down the height of this 4 over here, we're just going to note a little 0. So the height of this node is 0. Let's consider this 5 next. So here, this 5, again, like the 4, doesn't have any children. So its height, if it were a tree, is going to be 0. Let's consider the 3 next. The 3 doesn't have any children, so its height would be 0. Now let's look at this 2. So this 2 has 2 children. But in terms of actually the number of levels of children, it only has 1 level. And one way to see this is if you kind of want to see the number of levels, you can draw this horizontal line. You'll see there's only 1 line, so 1 level. The other way to see this is you see that this 2 has 2 children. It has a left child and a right child. And you want to see which of these, the left child or the right child, is a longer branch. In this case, they're both just a branch of 1. So we have 1 left child and 1 right child. So in this case, this 2, if we look at kind of the maximum of the left child versus the right child, both are 1, so the maximum is just 1. So it's a tree of height 1. And then finally, we have this 1 over here. And in this case, the height of this 1 is going to be 2. And the way to see that is if you look at the left child of this 1, you'll see that it has 2 layers of left children. So 1, 2. And then it only has 1 layer of a right child. So we just take the maximum of those 2. And so we get the height of this 1 is 2. So using this, what we can now do is we can actually look back at our final output, and there's something interesting to see here. So take a look at this vector over here. This vector contains 4, 5, and 3. And if you look at 4, 5, and 3, you'll see that all 3 of them have a height of 0. And this vector is at position 0. So it's at index 0 of the larger vector. If we look at 2, 2 has a height of 1, and it's at position 1 or index 1. And then finally, this 1 is at index 2, and it has a height of 2. So what you can see here is the height of the trees is actually going to help us figure out where to put them in the vector. So we're going to need some sort of get height function. So let's take a look at how we might code this. So I'll be doing this in C++, and here we have this find leaves function. It takes in a tree node pointer called root, and then it returns a vector of vectors. So that's this format here, something like this. I'm actually going to copy this. Let's copy the whole thing. Copy this over here. So we mentioned this notion of getting the height. So we're going to need some sort of get height function. So let's just start by declaring it. So we can call it just get height, and it's going to get the height of a node, assuming that node symbolizes a tree. So its input type should be a tree node pointer, so tree node star. We can call it root again. And then in terms of what it should return, it should probably just return an integer, get height, so that we actually know the height of this root node. Now, given this, let's take a look at how we kind of looked at our tree and how we were able to fill in the final vector. So ideally, this get height function, not only does it return the height, but it also knows where to put that node inside of our final vector. And to make this easier, why don't we just declare a global vector. So this global data structure, this is the one we're going to want to populate. We can call it answer, and we can declare it up here so that way it's visible everywhere. So in get height, the first thing we might want to do is we might want to just add kind of a base case. So in the case that root is empty. So in the case that root is empty, we probably just want to return something like -1. That tree just does not have a height. Again, there's no tree to begin with. So if it's a null pointer, which is how we're going to check if it's empty, we can just return -1. Now, the next thing is we actually need to determine the height of this root node. And so remember, the way that we talked about doing this is saying we're going to look at the left branch and the right branch of a node and find the one that's bigger. So what we can do is we can declare something like left height. And for now, we're just going to label it as x, and then right height. And again, we'll just for now label it as x. And the idea is our actual height, which I'm going to call height, is going to be the maximum of those two. So the maximum of left height and right height. Small typo there. Cool. So that's going to be our final height. And remember that we said now that we have the height, we can actually insert this node into our final answer, into this vector that we want to build up. And so what we can do here is use height to insert root. And so what we know is we know that this node is going to go at position height. So what we'll want to do is we'll want to do something like answer at index height. And then remember that that's going to return a vector. And so to add to a vector, we're going to need to use pushback. So we can use pushback. And then we want to push back this root value. So something like this 4, this 5, or this 3. And root is a pointer, so it's this pointer to this struct. So what we want to do is we want to access val. So we're just going to go root, arrow, val. So this should build up our tree as we want it. And then the last thing is we probably actually want to return height. Now, there are kind of two little things we need to keep in mind here. So remember that our answer vector starts totally empty. So given that it starts totally empty, this line is not valid in many cases. And so what we want to do is we want to check whether or not the subvector that we're interested in inserting in exists or not. So what we want to look for is this the first time that we're inserting a node of this height? So initialize vector for height if it doesn't exist. And so what we can do is we can actually just check this by saying if answer.size is going to give us the number of subvectors inside. If answer.size is equal to height, that means we've never inserted a vector of this size. And so in that case, what we'll want to do is we'll just want to do answer dot pushback, and then just we'll have an empty vector that we add in, and then we can use height to insert it, to insert the node after. The last thing we need to keep in mind is these x's. So right now these x's are just kind of freestanding x's. We're going to actually need to change those to something valid. What we want to do here is we have this getHeight function that actually can get us the height of a node. And so if we want to calculate the left height for this current root node, all we need to do is we just need to call getHeight on root left. And that will call getHeight on the left child of this root node. And then we can do a similar thing for getHeight of the right child of this node. So left height, right height, perfect. And then the last thing we need to do here is remember that the current height is going to include this node. So if we call getHeight on this node, this would kind of get the height of everything below the node. So we're just going to want to make sure that we add 1 in both cases. So, and then plus 1 here, using a semicolon. And so now this should actually get us the correct left height and the correct right height. So last thing we need to do is we just need to call this function, and then we should be good to go. So all we need to do is we can call getHeight, and we might want, just to kind of be safe, we might want to actually store the return value. So let's just call it return val, getHeight, and we want to call it on root. And that will make sure to populate this answer struct. And then we can just finally make sure that we return this answer. Okay, let's test it out. Cool. So looks like it worked. And yes, that's our final solution. Thanks for watching.